Earth is constantly being hit by something invisible. From every direction, at every moment, high-energy particles are raining down on our planet. They pass through the atmosphere, collide with air molecules, and send cascades of secondary particles streaming toward the surface. They have been doing this since long before humans existed, and for most of human history, we had no idea they were there at all. The first real evidence of these particles came in 1912, when an Austrian physicist named Victor Hess strapped scientific instruments to a hot air balloon and ascended to an altitude of 5,300 meters. He was investigating the rate of ionization in the upper atmosphere, essentially measuring how quickly atoms in the air were being stripped of their electrons. The prevailing assumption at the time was that this rate would decrease with altitude because scientists believed the source of ionizing radiation was the ground beneath them. Go high enough, the thinking went, and you would leave it behind. What Hess recorded instead completely contradicted that assumption. At 5,300 meters, the rate of ionization was 3 times higher than at sea level. Something above was responsible. Something in space. Hess had just discovered cosmic rays, and the discovery would eventually earn him a Nobel Prize in Physics in 1936. Cosmic rays are not rays in the traditional sense. They are high-energy particles, mostly protons that travel through the universe at velocities approaching the speed of light. When they reach Earth and slam into the upper atmosphere, they do not arrive quietly. The collision triggers a cascade, a so-called air shower, in which a single incoming particle can produce millions of secondary particles, muons, neutrons, electrons, positrons, and gamma rays, all spreading outward in a cone as they descend toward the ground. This is not a gentle process. The secondary particles produced by cosmic ray showers can interact with biological tissue, contributing to genetic mutations and incremental radiation damage over time. When they reach electronics in orbit, they can cause circuits to degrade, flip data bits, or fail catastrophically. Some of the most puzzling, unexplained errors in orbiting satellites have been attributed to cosmic ray interactions. The particles are not dangerous in any immediate, dramatic sense. The atmosphere absorbs most of the impact, but they are a persistent feature of life on Earth and a significant engineering challenge for spacecraft designers. What made cosmic rays particularly frustrating for scientists was not their effects, but their anonymity. Despite being discovered in 1912, the sources that produced them remained almost entirely unknown for more than a century. The reason comes down to a fundamental property of charged particles. Magnetic fields bend their paths. As cosmic rays travel through the galaxy, the magnetic fields threaded throughout interstellar space slowly deflect them, curving their trajectories away from the straight line that would point back to their origin. By the time they reach Earth, they have lost all directional memory of where they came from. Every clue about their origin has been erased. Scientists could measure how many cosmic rays arrived, and at what energy they could study what they were made of. But finding out where they came from was a different problem entirely, one that required an entirely different approach. When physicists plot the number of incoming cosmic rays against their energy, they produce a spectrum, a graph that reveals how the population of these particles changes across different energies. For most of the spectrum, the relationship is smooth and predictable. As energy increases, the number of particles decreases in a steady, proportional way. But at a certain point, specifically at around 4 peta-electron-volts, where 1 peta-electron-volt equals 1 quadrillion electron-volts, the graph takes a sudden turn. The drop-off becomes steeper. Cosmic rays above this energy become far more rare. This feature has been called the knee of the cosmic ray spectrum. Its significance has been debated for decades. Some scientists propose that the knee marks the upper limit of what sources inside the Milky Way can produce, meaning that the cosmic rays above this threshold must be coming from other galaxies. Others were less certain. But without any way to trace the particles back to their origins, the debate could not be settled by observation. It remained theoretical. What the field needed was a new kind of observatory, not a telescope designed for visible light, or even for X-rays, but something designed specifically to catch the highest energy particles in the universe and extract information from the debris they leave behind. The Large High Altitude Air Shower Observatory, known as LHAASO, was constructed for exactly this purpose. It sits at an altitude of nearly 4,500 meters above sea level in the mountains of Sichuan Province, China. The altitude matters because the air is thinner there, which means cosmic ray showers develop lower in the atmosphere, closer to the detectors. More of the shower can be captured and measured before it spreads too thin to detect. The scale of the facility reflects the rarity of the particles it is hunting. The highest energy cosmic rays are extraordinarily uncommon. For particles at the very top of the energy spectrum, scientists estimate that fewer than 1 per square kilometer per century will ever strike Earth. To have any hope of catching them in a reasonable time frame, you need a detector that covers an enormous area. LHAASO covers the equivalent of 190 football fields. The observatory does not look like a traditional telescope. There is no dish, no lens, no mirror. Instead, LHAASO uses an interconnected array of at least 3 different types of detectors spread across its vast footprint. Each type is designed to capture a different component of the particle shower produced when a cosmic ray hits the atmosphere. By combining the signals from all of them, scientists can reconstruct the shower working backward from the debris to identify what the original particle was, how much energy it carried, and approximately where in the sky it came from. Professor Zheng Cao, the chief scientist of the LHAASO mission, described the core challenge. To make good measurements at the knee of the cosmic ray spectrum, the detector must be big enough, and it must be able to identify the original particle from the air shower it creates. LHAASO was designed to meet both of those requirements, and it did not take long for results to arrive. The observatory was still being completed when the first major discovery came. With roughly half of the facility built and operational for only about 6 months, scientists began noticing something unexpected in the data. There were far more gamma rays than anticipated gamma rays, with energies that exceeded anything previously recorded. Gamma rays are photons, particles of light, but with energies millions or billions of times higher than visible light. Unlike charged particles such as protons, photons carry no electric charge. This is critical. Because they have no charge, gamma rays are not deflected by magnetic fields. They travel in straight lines. When a gamma ray arrives at a detector on Earth, the direction it came from is preserved. It is still pointing, essentially, back toward its source. By 2021, LHAASO had detected gamma-ray photons with energies exceeding 1 peta-electron-volt, equivalent to 1 quadrillion electron-volts. One photon in particular registered an energy of 1.4 peta-electron-volts, making it the highest energy photon ever recorded by any instrument in history. For comparison, the Large Hadron Collider at CERN, the most powerful particle accelerator ever built by humans, accelerates protons to energies of roughly 6.5 tera-electron-volts per beam. 1 peta-electron-volt is 1,000 tera-electron-volts. The photon LHAASO detected carried nearly 150 times more energy than the fastest proton CERN has ever produced. The laws of physics do not allow particles to simply appear with enormous energy from nothing. Energy must be transferred. Something had to accelerate these particles, pouring that colossal amount of energy into them. For decades, theorists had predicted that such sources must exist in the universe, even though none had ever been conclusively confirmed. They were called PeVatrons objects, capable of accelerating particles to energies of at least 1 peta-electron-volt. LHAASO's observations proved that PeVatrons were real. The search for individual PeVatrons then began in earnest. Because gamma rays point back toward their sources, they offered a practical trail to follow. Scientists could look at where the highest energy gamma rays were coming from and identify which objects in those regions were plausible candidates. The challenge was that gamma rays indicated general direction, not an exact distance, and many regions of the sky contain multiple energetic objects. Sorting out which one was responsible required careful analysis. By 2021, LHAASO had identified 12 candidate PeVatron sources. Each one represented a place in the galaxy where something was accelerating particles to extreme energies, releasing gamma rays as a byproduct. But what were these sources? What mechanism could possibly produce accelerations on this scale? To understand that, it helps to understand one of the most well-established mechanisms for accelerating particles in astrophysical environments: diffusive shock acceleration. When a massive star reaches the end of its life and explodes as a supernova, it releases an enormous shock wave that expands outward into the surrounding gas at speeds of thousands of kilometers per second. Charged particles can become trapped in this shock wave, bouncing back and forth across the boundary between the fast-moving shock material and the slower material ahead of it. Each time a particle crosses this boundary, it gains a small amount of energy. Cross it enough times, and the cumulative energy gain becomes very large. This process, diffusive shock acceleration, has long been considered one of the primary ways that cosmic rays are accelerated throughout the galaxy. Supernova remnants, the expanding shells of gas left behind after a stellar explosion, are the most natural candidates for this process. And one of the most famous and well-studied supernova remnants is Messier 1, also known as the Crab Nebula, located about 6,500 light-years from Earth in the constellation Taurus. The Crab Nebula is the remnant of a supernova that was observed by astronomers in 1054. At its center sits the Crab pulsar, a rapidly rotating neutron star, the ultra-dense collapsed core left behind when the original star exploded. The pulsar rotates 30 times per second, and as it does, it generates a powerful wind of charged particles that streams outward into the surrounding nebula. This pulsar wind nebula is one of the most studied objects in high-energy astrophysics and has served as a calibration standard for gamma-ray observatories for decades. In the gamma-ray domain, the Crab Nebula displays extreme variability. It produces intense flares, lasting anywhere from a few hours to several days, during which its gamma-ray output spikes dramatically. With the new understanding of PeVatrons, scientists recognized that these flares were the signature of serious electron acceleration happening within the system. Exactly what drives this acceleration is still a matter of active investigation. It could be diffusive shock acceleration at the boundary between the pulsar wind and the surrounding medium, or it could involve energy released when magnetic field lines break and reconnect in a process called magnetic reconnection. There may also be more complex mechanisms at work within the pulsar wind itself. What is clear is this: at high energies, electrons can transfer part of their energy to background photons, low-energy photons, that are scattered to much higher energies through a process called inverse Compton scattering. This is how peta-electron-volt electrons produce the peta-electron-volt gamma rays that LHAASO detects. For these interactions to produce gamma rays at 1 quadrillion electron volts, the electrons doing the accelerating must have started with several times that energy. This makes the Crab Nebula an unambiguous PeVatron, and a particularly powerful one. However, there is an important caveat. This has been demonstrated specifically for electrons, not for protons. In particle physics terminology, electrons belong to a family of particles called leptons, so a source that primarily accelerates electrons is called a leptonic accelerator. Cosmic rays, however, are mostly protons, which belong to a family of particles called hadrons. The PeVatrons most relevant to understanding the origin of cosmic rays are hadronic accelerators, sources that accelerate protons to peta-electron-volt energies. Finding hadronic PeVatrons requires identifying specific signatures in the gamma-ray spectrum that can only be produced by proton acceleration, as opposed to electron acceleration. This distinction is crucial, and it drove scientists to look beyond the Crab Nebula to other candidate sources. Which brings us to the 1.4 peta-electron-volt photon, the highest energy photon ever detected. Scientists traced its origin to the Cygnus region of the sky. The constellation Cygnus is one of the most recognizable in the northern hemisphere, and the region of the galaxy it corresponds to is exceptionally active. Cygnus spans more than 800 square degrees of sky, equivalent to the area covered by roughly 4,000 full moons. And within it, LHAASO found high concentrations of peta-electron-volt photons clustering inside a structure known as the Cygnus cocoon. The Cygnus cocoon is a massive superbubble, a vast cavity in the interstellar medium shaped by the combined winds and radiation of many massive, hot, young stars. At its center is the Cygnus OB2 association, a star cluster containing hundreds of massive young stars, all blowing powerful stellar winds. Located roughly 5,000 light-years from Earth, the association is one of the most powerful concentrations of young massive stars in the Milky Way. The combined effect of all these stellar winds creates a high-pressure environment capable of accelerating particles to extreme energies. LHAASO's observations of the Cygnus region also revealed gamma-ray signals consistent with a very different kind of object, Cygnus X3, an X-ray binary system. An X-ray binary is a system in which two objects orbit each other closely, in this case, a compact object and a donor star. The donor star in Cygnus X3 is a Wolf-Rayet star, meaning it is extremely hot, extremely massive, and blowing off material at a tremendous rate through strong stellar winds. The compact object, most likely a black hole, though a neutron star cannot be ruled out, feeds on material streaming from the donor star and releases powerful jets of plasma in the process. Jet-producing systems like this create conditions that theorists have long considered favorable for particle acceleration. The jets, moving at substantial fractions of the speed of light, can interact with surrounding material and generate the kind of shock waves needed to boost particles to very high energies. Initially, scientists could not determine whether the peta-electron-volt gamma rays from the Cygnus region were coming from the star cluster OB2 or from the binary system Cygnus X3. The signals overlapped in direction, and without a way to distinguish between them, both remained candidate sources. The answer came from a closer inspection of the signal itself. Scientists noticed that the gamma ray flux was not constant. It varied, and it varied with a precise period of 4.8 hours. The same period appeared not only in the gamma rays, but also in X-ray and infrared observations of the same region. That periodicity was the key. Cygnus X3 is a binary system, and the orbital period of the compact object around its Wolf-Rayet companion is exactly 4.8 hours. The gamma rays were pulsing in sync with the orbit, which meant they could only be coming from Cygnus X3. This identification was scientifically significant for several reasons. The highest energy photons from Cygnus X3 reached 3.7 peta-electron-volts. Because the gamma rays are produced by proton interactions, and because the protons must carry several times the energy of the photons they produce, this implies that the protons inside Cygnus X3 had been accelerated to energies of at least 10 peta-electron-volts. That makes Cygnus X3 not just a PeVatron, but a super PeVatron, an object accelerating protons to energies an order of magnitude above the threshold, reaching deep into the regime that was once thought to be impossible for galactic sources. X-ray binaries like Cygnus X3 had been studied for decades, but the discovery of their role as particle accelerators on this scale was not anticipated. It added an entirely new category of object to the list of things capable of producing the highest energy cosmic rays. The discoveries kept coming. LHAASO published its first comprehensive catalog of galactic PeVatrons in 2023, listing 43 ultra-high energy gamma ray sources distributed across the Milky Way. Within 2 years, continued monitoring by LHAASO and several other observatories around the world pushed that number above 75 candidate PeVatrons within our own galaxy. The implications of this are significant. For many decades, astronomers considered the Milky Way a relatively calm, stable place. Unlike some galaxies, the Milky Way does not have an extraordinarily active core. Its central black hole, Sagittarius A star, is comparatively quiet compared to the supermassive black holes that drive the violent, luminous activity seen in quasars and blazars in distant galaxies. This led to a general impression that our galaxy, while complex and interesting, was not particularly extreme in terms of energy. LHAASO's catalog fundamentally overturned that picture. More than 75 particle accelerators operating at peta-electron-volt energies scattered throughout the galaxy, in star clusters, supernova remnants, pulsar wind nebulae, and binary systems describe a galaxy that is constantly producing particles at energies far beyond anything achievable by human technology. The Milky Way is not a quiet place. It is filled with natural particle accelerators, many of them producing cosmic rays that have been raining down on Earth for billions of years. The discovery of PeVatrons also reframes the long-standing mystery of the cosmic ray knee. If PeVatrons are distributed throughout the Milky Way and are capable of accelerating protons to at least 1 peta-electron-volt, and in some cases well beyond, then the knee of the cosmic ray spectrum may not mark the boundary between galactic and extragalactic sources. Instead, it may reflect the maximum energy typical galactic accelerators can reach. The super PeVatrons like Cygnus X3 push beyond that limit, but they may be relatively rare compared to the broader population. Sorting out the exact contribution of different source types to the overall cosmic ray spectrum remains an active area of research. The spectrum itself needs to be measured with better precision at the highest energies, and the individual sources need to be characterized in more detail specifically, whether they are leptonic or hadronic accelerators, and how the energy gets distributed among different particle types. This is where international collaboration is becoming increasingly important. LHAASO is working alongside several other high-energy gamma-ray observatories spread across multiple countries, including facilities in the United States, Germany, Namibia, and Spain. These observatories use complementary techniques and observe gamma rays across different energy ranges, allowing scientists to build up a more complete picture of the photon spectrum from the lowest to the highest detectable energies. Some observatories operate on the ground, using the same air shower detection approach as LHAASO. Others detect gamma rays from space, above Earth's atmosphere, where the signal does not need to be reconstructed from secondary particles. Together, they provide overlapping coverage that allows scientists to verify detections across multiple instruments and build confidence in their conclusions. The data-sharing culture that has developed among these groups reflects the scale of the problem. No single observatory can cover all energies, all sky positions, and all particle types simultaneously. The catalog of PeVatrons is a collective product, not the result of any one experiment. One aspect of cosmic ray research that remains particularly challenging is neutrino astronomy. When protons are accelerated to high energies and collide with surrounding gas or radiation, they produce not only gamma rays, but also neutrinos, nearly massless particles that carry no charge and interact almost not at all with matter. Neutrinos are appealing from a scientific perspective because, like gamma rays, they travel in straight lines and preserve directional information. Unlike gamma rays, they pass through almost everything without being absorbed, meaning they can potentially escape from regions deep inside dense environments where gamma rays cannot. However, detecting neutrinos is extraordinarily difficult. Facilities like the IceCube Neutrino Observatory, embedded in the Antarctic ice sheet, have begun to detect high-energy neutrinos from astrophysical sources, and some of those signals appear to correlate with known gamma-ray emitters. If those correlations are confirmed, they would provide direct, independent evidence that the gamma-ray sources are also producing cosmic rays, the hadronic signature that scientists are most eager to confirm. The connection between gamma-ray observations and neutrino observations could become one of the most powerful tools for identifying true hadronic PeVatrons, the objects most directly responsible for the cosmic rays that have been raining down on Earth since Hess first detected them from a balloon. In 1912, understanding PeVatrons also connects to questions about the large-scale structure of the galaxy. Cosmic rays are not simply accelerated and then absorbed nearby. They spread out through the galaxy, interacting with magnetic fields and gas, and contributing to the broader energy balance of the interstellar medium. The total energy carried by cosmic rays throughout the Milky Way is comparable to the energy in the galaxy's magnetic field and the energy in the thermal motions of interstellar gas. They are not a minor component, they are a major player in how energy flows through the galaxy. If PeVatrons are the primary factories producing the highest energy portion of this cosmic ray population, then understanding where they are and how they work is essential for understanding the energy structure of the galaxy itself. A galaxy with more than 75 active PeVatrons is a galaxy with a constant, vigorous injection of ultra-high energy particles into the interstellar medium. Those particles spread, lose energy gradually, and eventually become part of the broader cosmic ray background that Victor Hess first detected more than a century ago. The variety of objects confirmed or suspected as PeVatrons is also scientifically interesting in its own right. Supernova remnants, pulsar wind nebulae, stellar clusters, X-ray binaries, these are not similar objects. They operate through different physical mechanisms, involve different timescales, and exist in very different environments. Yet all of them appear capable of producing particles at peta electron-volt energies. This suggests that extreme particle acceleration is not a rare or specialized phenomenon requiring very particular conditions. It emerges from multiple pathways across a wide range of environments. The common thread appears to be the presence of shocks, strong magnetic fields, and a sustained energy source capable of continuously feeding the acceleration process. Whether that energy source is a rotating neutron star, a stellar wind, an accretion disk, or the aftermath of a supernova explosion, the outcome can be the same. Particles pushed to energies that dwarf anything produced by human technology. One of the most consequential open questions is whether the galaxy produces cosmic rays above the so-called ankle, the energy at which the spectrum begins to flatten again at very high energies, around 1 tera-electron-volt. Above the ankle, the cosmic ray flux becomes dominated by particles thought to originate outside the Milky Way, from sources in other galaxies. These extragalactic cosmic rays are even more energetic than the peta-electron-volt particles LHAASO has been studying. Their origins are even less understood, and tracking them poses even greater challenges given the distances involved. Some of the most powerful known astrophysical objects, active galactic nuclei, gamma-ray bursts, galaxy clusters, are candidates for the sources of these ultra-high-energy cosmic rays. But connecting individual detected particles to specific distant sources requires even more precise measurements and larger detector arrays than currently exist. Several next-generation observatories are being developed to push the frontier further. The Cherenkov Telescope Array, a major international facility currently in the construction phase, will consist of dozens of telescopes distributed across 2 sites, one in the northern hemisphere in La Palma, Spain, and one in the southern hemisphere in Chile. The array will observe gamma rays with greater sensitivity and over a wider energy range than any previous ground-based instrument. In combination with LHAASO and other existing facilities, the Cherenkov Telescope Array is expected to dramatically expand the catalog of PeVatrons, refine the measurements of individual sources, and potentially identify the first confirmed hadronic PeVatrons through the combination of gamma-ray and neutrino observations. There are also proposed upgrades to LHAASO itself, and discussions about building similar high-altitude air shower arrays in other parts of the world, which would allow scientists to observe more of the sky and maintain continuous monitoring of transient sources like flaring pulsars and binary systems. The field of high-energy astrophysics has been transformed in a relatively short period. As recently as 2020, no PeVatron had been conclusively detected. By 2023, more than 40 had been identified. By 2025, the number exceeded 75. This is not a slow accumulation of knowledge. It is a rapid, sustained expansion of our understanding of what the galaxy is capable of. At the heart of all of this is a question that Victor Hess's balloon flight raised in 1912 and that generations of physicists have been trying to answer ever since. Where does the energy come from? The answer, it turns out, is spread throughout the galaxy in dozens of sites, each operating at energies that push against the limits of known physics. Rotating neutron stars pour energy into particle winds. Binary systems drive jets of plasma that produce shock waves. Massive star clusters blow stellar winds that intersect and collide and accelerate particles over vast distances. Supernova shock waves expand for tens of thousands of years, continuously adding particles to the galactic reservoir. The Milky Way is not a quiet background for human civilization. It is an energetic, dynamic environment, filled with particle accelerators whose outputs have been washing over Earth since long before life began. What has changed is that we can now detect those outputs, trace them back toward their sources, and begin to understand the mechanisms that drive them. The cosmic rays Victor Hess discovered are still arriving. Every second, high-energy particles are entering Earth's atmosphere, triggering cascades and raining secondary particles toward the surface. But now, for the first time, scientists can follow the trail in reverse from the particle shower on the ground through the gamma rays that point back across thousands of light years to the objects that started the whole process. What the next generation of observatories will reveal is not yet known. But the pattern of the last few years, each new measurement expanding the catalog, each new source revealing a new acceleration mechanism, suggests that the most complete picture of cosmic ray origins is still ahead of us. The galaxy is more powerful, more active, and more interesting than it appeared even a decade ago. And the instruments being built right now are designed to keep pulling back that curtain, revealing more of what has been there all along, invisible and energetic and impossible to ignore. The nature of cosmic rays themselves, their composition, their range of energies, and their behavior tells a story that took decades to piece together. When Victor Hess confirmed that ionizing radiation was streaming in from space in 1912, scientists initially imagined these cosmic rays as electromagnetic radiation, similar to X-rays, but more energetic. The term ray reflected that assumption. But over the following decades, a more complex picture emerged. By the 1930s, physicists established that at least some cosmic rays were deflected by Earth's magnetic field in ways that only charged particles would be. The cosmic radiation Hess had discovered was not primarily photons. It was particles, protons, atomic nuclei, and electrons carrying kinetic energy on a scale that had no precedent in any laboratory on Earth. The composition of cosmic rays varies across different energy ranges. At lower energies, they are mostly protons, the nuclei of hydrogen atoms, stripped of their electrons. At higher energies, heavier nuclei become more prominent. Helium nuclei, the next lightest after hydrogen, make up a significant fraction of the cosmic ray flux. Carbon, oxygen, iron, all have been detected. The heavier the nucleus, the more complex the dynamics of its acceleration and propagation through the galaxy. Iron nuclei, for example, are among the heaviest commonly detected cosmic ray components. An iron nucleus contains 26 protons and typically 30 or more neutrons, giving it an atomic mass of around 56. When physicists describe the energy of a cosmic ray particle, they typically refer to the total kinetic energy, not energy per unit of charge. A single iron nucleus with an energy of 1 peta-electron-volt carries the same total kinetic energy as a proton at the same energy. But because the iron nucleus has 26 times the charge of a proton, it only needs to be accelerated through a voltage of roughly 38 tera-electron-volts per unit charge to reach that energy. This matters because the efficiency of acceleration mechanisms often scales with charge-heavier nuclei, may be easier to push to high total energies than protons, under the right conditions. This compositional complexity is one reason why identifying cosmic ray sources from the particles alone is so difficult. Even if you could measure the direction of a cosmic ray precisely, knowing it was an iron nucleus tells you something different than knowing it was a proton. The two particles could have been accelerated by completely different mechanisms and traveled very different paths. The energy spectrum of cosmic rays spans an extraordinary range from roughly 1 giga-electron-volt, similar to the energies produced by the sun's activity during solar flares, all the way up to beyond 100 exa-electron-volts, more than 100 billion electron-volts, for the most extreme particles ever detected. This range spans more than 11 orders of magnitude. For comparison, the full range of audible sound spans only about 3 orders of magnitude. The cosmic ray energy spectrum covers energies that differ by a factor of 100 billion. Across most of this range, the spectrum follows a smooth power law, a mathematical relationship where the number of particles drops off in a consistent proportional way as energy increases. But there are notable deviations. The knee, around 4 peta-electron-volts, is 1. There is also a feature at around 1 exa-electron-volt called the ankle, where the spectrum flattens slightly before steepening again. And at the very highest energies, above about 50 exa-electron-volts, there is a sharp cutoff, in the point where almost no particles are detected at all. This high-energy cutoff was predicted theoretically in 1966, independently by 3 physicists, Kenneth Greisen in the United States, and Vadim Kuzmin and Georgy Zatsepin in the Soviet Union. The prediction, now called the Greisen-Zatsepin-Kuzmin limit, or the GZK limit, arises from the interaction of ultra-high-energy cosmic rays with the cosmic microwave background, the faint thermal radiation that fills all of space as a remnant of the early universe. When a proton at extremely high energy collides with one of these microwave photons, the interaction can produce new particles, specifically pions, which drains energy from the proton. Above a certain energy threshold, this energy loss becomes so rapid that protons cannot travel more than about 50 megaparsecs, roughly 160 million light-years, without losing enough energy to fall below the threshold. The GZK limit effectively means that the highest energy cosmic rays we detect must originate relatively nearby, on cosmological scales. The observation of particles that appeared to violate or come close to the GZK limit detected by the LHAASO observatory in Japan in the 1990s created considerable controversy and sparked debates about whether new physics might be needed. Later, more sensitive experiments found that the flux of ultra-high-energy cosmic rays does indeed drop sharply at around the predicted energy, consistent with the GZK suppression. But the sources of these particles, arriving from within the roughly 150 million light-year radius where they could have originated, remain largely unidentified. The question of cosmic ray origins, at all energies, not just the highest, has required scientists to build and operate increasingly sophisticated instruments and to think carefully about what signatures would distinguish different types of sources. One of the most important tools in this investigation, and the one that opened the door to the PeVatron era, is multi-messenger astronomy. For most of the history of astronomy, observations were made in a single messenger, light. Astronomers studied stars, nebulae, and galaxies through their electromagnetic radiation, whether visible, infrared, ultraviolet, X-ray, or radio. The universe was understood through what it emitted as light. Beginning in the 20th century, cosmic rays themselves became a second messenger particles rather than photons, carrying information from space, but losing that information through magnetic deflection before reaching Earth. The situation changed dramatically in the early 21st century. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LHAASO, detected gravitational waves for the first time, ripples in spacetime produced by the merger of two black holes. 2 years later, LHAASO detected gravitational waves from the merger of two neutron stars at almost the same moment that telescopes around the world detected a gamma-ray burst from the same location. For the first time, a single astronomical event had been observed through two completely independent physical signals, gravitational waves and electromagnetic radiation. Multi-messenger astronomy had arrived. For cosmic ray research, the equivalent breakthrough involves combining gamma-ray observations with neutrino detections, and eventually with gravitational wave observations for appropriate source types. Each messenger carries different information and escapes from different environments. Together, they allow scientists to see sources from multiple angles simultaneously. LHAASO's gamma-ray observations represent one prong of this multi-messenger approach. The IceCube Neutrino Observatory in Antarctica represents another. IceCube consists of more than 5,000 optical sensors embedded in a cubic kilometer of transparent Antarctic ice, designed to detect the faint flashes of light produced when high-energy neutrinos occasionally interact with ice molecules. When such an interaction occurs, it produces a charged particle that travels faster than light travels through ice, which is slower than light travels through vacuum. And this produces a cone of blue light called Cherenkov radiation, which the sensors detect. IceCube has been accumulating data since its completion in 2010, and over the years it has built up a catalog of high-energy astrophysical neutrinos, with energies ranging from tera-electron-volts to peta-electron-volts. In 2023, IceCube published a landmark result: a statistically significant excess of neutrinos from the direction of the Milky Way's galactic plane, consistent with cosmic ray interactions producing neutrinos throughout the galaxy. This was the first time the Milky Way had been detected as a neutrino source. Some of the individual neutrino detections in IceCube's catalog overlap spatially with sources in LHAASO's PeVatron catalog. These are not yet confirmed associations. The positional uncertainty in neutrino detection is typically larger than in gamma-ray detection, but the overlap suggests that some PeVatrons are indeed hadronic, producing both gamma rays and neutrinos through proton-proton interactions. Confirming this connection is one of the highest scientific priorities in the field. A source detected in both high-energy gamma rays and high-energy neutrinos would be unambiguous evidence of hadronic acceleration protons being pushed to peta-electron-volt energies and then interacting with surrounding material. This would directly link the source to the cosmic rays that have been arriving at Earth since long before anyone thought to look for them. The physics of hadronic versus leptonic acceleration is worth examining in more detail, because the distinction matters deeply for understanding what is actually happening in these extreme environments. When a proton is accelerated to very high energies and then collides with another proton or with a gas nucleus, The collision produces a shower of secondary particles. Among these are particles called pions, which come in positive, negative, and neutral varieties. Neutral pions are unstable and decay almost immediately into 2 gamma-ray photons. This is the principal way that hadronic accelerators produce gamma rays. The gamma-ray photons inherit a fraction of the original pion's energy, and since the pions come from proton collisions, the gamma rays trace the proton activity. Charged pions, meanwhile, decay into muons and neutrinos. The muons subsequently decay into electrons and more neutrinos. This is why hadronic sources produce not just gamma rays but also neutrinos. The ratio between gamma rays and neutrinos from this process is predictable, which means that measuring both signals from the same source allows scientists to test whether the observed emissions are consistent with hadronic physics. The alternative is leptonic emission, driven by electrons rather than protons. High-energy electrons can emit gamma rays through 2 main processes. In synchrotron radiation, electrons spiraling through magnetic fields lose energy as photons. In inverse Compton scattering, electrons transfer energy to lower-energy photons, boosting them into the gamma-ray range. Neither of these processes produces neutrinos in any detectable quantity. So, a source emitting gamma rays but no neutrinos, or far fewer neutrinos than the hadronic model predicts, is likely leptonic. The Crab Nebula is the canonical leptonic accelerator, with its gamma-ray emission well explained by electrons accelerated in the pulsar Wind Nebula. Most PeVatrons identified by LHAASO have not yet been definitively classified. For many, both leptonic and hadronic models can fit the gamma-ray data. Breaking the degeneracy requires neutrino observations. This challenge is why IceCube's eventual successor, IceCube Gen 2, is one of the most eagerly anticipated projects in the field. IceCube Gen 2 is planned to expand the instrumented volume of the Antarctic detector by roughly 8 times, greatly increasing its sensitivity to astrophysical neutrinos. With more neutrino events, scientists will be able to look for correlations with individual sources rather than just with broad regions of the sky, potentially identifying specific hadronic PeVatrons for the first time through neutrino emission. The timescale for IceCube Gen 2 is roughly the late 2030s, though planning and development are already underway. Combined with the Cherenkov Telescope Array, which should reach full operation in the late 2020s, the next decade promises a dramatic expansion in observational capability at the highest energies. Beyond individual source identification, one of the broader questions in the field concerns how cosmic rays propagate through the galaxy after they are accelerated. The interstellar medium is not empty. It is filled with gas, dust, magnetic fields, and radiation. Cosmic rays traveling through it interact with all of these. Magnetic fields cause cosmic ray trajectories to curve. The higher the energy of the particle, the less it is deflected by a given magnetic field strength. This is why ultra-high-energy cosmic rays, those above about 10 electron-volts, can still retain some directional information when they reach Earth, while the cosmic rays at peta-electron-volt energies that LHAASO's detecting are completely scrambled. For the peta-electron-volt particles, the only way to track their origin is through the secondary gamma rays and neutrinos produced along the way. Cosmic rays also lose energy as they propagate. They collide with gas molecules, producing new particles and losing some kinetic energy. They interact with the cosmic microwave background and other radiation fields. At the highest energies, these losses are rapid. At lower energies, the losses are slower, and cosmic rays can survive for millions of years, diffusing throughout the galaxy before losing enough energy to become undetectable. This long diffusion time means that the cosmic rays reaching Earth carry a mixture of contributions from many different sources, at many different distances, accumulated over millions of years of galactic history. Disentangling this mixture and attributing specific components of the observed spectrum to specific source populations is one of the most complex problems in astrophysics. Models of cosmic ray propagation are tested against observations of diffuse gamma-ray emission throughout the galaxy. When cosmic rays interact with interstellar gas, they produce pions and subsequently gamma rays, just as in individual PeVatron sources. But this happens throughout the galactic disk, wherever cosmic rays are present. The resulting diffuse gamma-ray glow of the galaxy encodes information about the distribution and energy spectrum of cosmic rays, far from individual sources. LHAASO has also contributed to measuring this diffuse emission at peta-electron-volt energies, providing constraints on how cosmic rays spread through the galaxy after leaving their sources. Combined with observations from other instruments and with models of the galactic magnetic field and gas distribution, these measurements are gradually building a more complete picture of the cosmic ray ecosystem. One of the most intriguing recent findings in this context involves the region around the center of the Milky Way. The galactic center is the most energetically dense region of the galaxy, home to the supermassive black hole Sagittarius A star, thousands of massive stars, strong magnetic fields, and intense radiation fields. It is also one of the brightest regions of the sky in gamma rays. Whether some of the gamma ray emission from the galactic center comes from dark matter annihilation, from cosmic ray interactions, from individual sources too closely packed to resolve, or from some combination of these, has been actively debated. LHAASO and other high-energy observatories have detected gamma-ray emission from the galactic center at peta-electron-volt energies, suggesting that something in or near the galactic center is acting as a PeVatron. Sagittarius A star itself, while relatively inactive by extragalactic standards, may have been considerably more active in the relatively recent galactic past, on timescales of millions of years. Some models suggest that a past active phase could have injected a large population of high-energy cosmic rays into the central region that are still present today. The Fermi bubbles, enormous lobes of gamma-ray emission extending above and below the galactic plane by about 25,000 light-years, may be a signature of this past activity. They were discovered in 2010 using data from the Fermi Gamma-Ray Space Telescope, and their origin, whether driven by a past active phase of Sagittarius A star, by intense star formation, or by some combination, is still being debated. Their connection, if any, to the PeVatrons found throughout the galactic disk is not established. These questions are connected by a common thread. The Milky Way has a history of energetic activity, and understanding the current population of cosmic rays requires accounting for that history. The cosmic rays arriving at Earth today are not just a snapshot of the current sources, they carry traces of sources that existed millions of years ago. The observational challenge is to extract that history from the current measurements. This requires not only more sensitive detectors, but also better theoretical models, better simulations of cosmic ray propagation, and better measurements of the galactic magnetic field structure, which governs how cosmic rays diffuse and lose energy over time. Progress on all of these fronts is happening simultaneously. The next decade will bring better instruments, larger catalogs of sources, more neutrino detections, and improved propagation models. The synthesis of all this information promises to deliver, for the first time, a genuinely comprehensive account of how energy flows through the Milky Way on galactic scales. Victor Hess measured an ionization rate 3 times higher than expected at an altitude of 5,300 meters in 1912. In the century plus since that discovery, scientists have traced the energy behind that ionization through layers of increasingly extreme physics, from charged particles deflected by magnetic fields, to gamma-ray photons pointing back across thousands of light-years, to neutrinos that pass through entire planets without noticing, to gravitational waves that ripple through space-time itself. The cosmic rays that prompted his original observation are still arriving. The sources that produce them have been identified as some of the most energetic objects in the galaxy. The mechanisms that drive them are being connected, with increasing precision, to fundamental physics processes operating at the extreme end of what nature allows. The question is no longer whether the Milky Way contains particle accelerators capable of producing peta-electron-volt particles. We know that it does more than 75 of them, and counting. The question is how they work in detail. Which of them are responsible for which components of the cosmic ray spectrum, and what happens to the particles they produce as they spread through the galaxy over millions of years? These are hard questions. They require instruments that do not yet exist, theoretical tools that are still being developed, and observational data sets that will take years to accumulate. But the pace of discovery over the last 5 years, from 0 confirmed PeVatrons to more than 75, from theoretical predictions to observational reality, suggests that the next 5 years will be at least as revelatory. The universe, it turns out, is a far more energetic place than it looks from the surface of a planet, shielded by an atmosphere and a magnetic field. The energy Victor Hess measured was a whisper of what was really out there. The full sound of it, the peta-electron-volt shock waves, the pulsar winds, the jet-driven plasma, the stellar clusters, blowing their winds into space for millions of years, is still being heard for the first time. To truly appreciate how remarkable the discovery of PeVatrons is, it helps to understand just how difficult accelerating particles to peta-electron-volt energies actually is, and why physicists spent decades doubting it was possible for any source within the Milky Way. The Large Hadron Collider at CERN is the most powerful particle accelerator ever built by human civilization. It occupies a circular tunnel, 27 kilometers in circumference, buried beneath the Swiss-French border near Geneva. It uses superconducting magnets operating at temperatures colder than outer space to steer beams of protons around its ring, and it collides those beams at energies of up to 13 tera-electron-volts in the center of mass, that is, 13 trillion electron-volts. The facility cost roughly $10 billion to construct and requires the collaboration of thousands of physicists, engineers, and technicians from more than 100 countries to operate. And yet the highest photon LHAASO detected carries 1.4 peta-electron-volts of energy, more than 100 times the energy achievable at CERN. The protons that produced it must have had even more. Whatever produced those protons did not need tunnels 27 kilometers around, or billions of dollars of superconducting magnets. It used the natural physics of extreme astrophysical environments, shocks, magnetic fields, plasma jets, to achieve what no human engineering has come close to matching. This is not simply a fact about scale. It is a fact about the physical mechanisms of acceleration. At CERN, particles are accelerated by radiofrequency electric fields, applied precisely as the particles orbit the ring. The process is controlled, well understood, and meticulously engineered. In contrast, astrophysical particle acceleration is messy, turbulent, and operates across vast regions of space and time. The fact that it nonetheless achieves higher energies than our most sophisticated engineering reflects how the universe can leverage enormous spatial scales and sustained energy sources in ways that are simply not available to any human. Technology. Diffusive shock acceleration, the most commonly invoked astrophysical mechanism, works because a particle does not need to gain all its energy in a single interaction. Each crossing of a shock front adds a small increment of energy. Cross the shock 100 times, 1,000 times, 10,000 times, and the cumulative gain becomes enormous. The particle bounces back and forth, trapped by magnetic fields on both sides of the shock, each crossing adding to its energy budget. The process is probabilistic. Some particles escape before gaining much energy, others stay long enough to reach very high energies. The resulting energy spectrum is a power law, matching what is actually observed in cosmic ray data. But diffusive shock acceleration has a natural limit. At some point, the particle's gyroradius, the radius of the circular path it follows in the magnetic field, becomes so large that it can no longer be confined by the shock. The particle escapes, and acceleration stops. The maximum energy a shock can produce depends on the magnetic field strength, the shock velocity, and the physical size of the acceleration region. For typical supernova remnant parameters, models predict maximum energies of around 1 peta-electron-volt for protons. Beyond that, particles escape before reaching higher energies. This is one reason why the knee of the cosmic ray spectrum, at around 4 peta-electron-volts, was long associated with the maximum energy of galactic sources, specifically supernova remnants. The knee was thought to mark the boundary beyond which the galaxy could not accelerate particles further. Cosmic rays above the knee, in this view, came from extragalactic sources. LHAASO's discoveries have complicated this picture significantly. The detection of super PeVatrons like Cygnus X3, capable of accelerating protons to at least 10 peta-electron-volts, shows that the galaxy contains sources that exceed the standard supernova remnant limit. These sources must be operating through mechanisms that allow more extreme confinement or more sustained acceleration than a typical supernova remnant provides. For X-ray binaries like Cygnus X3, the jets of plasma launched by the compact object are a plausible candidate mechanism. These jets can reach velocities of tens of thousands of kilometers per second, a substantial fraction of the speed of light. At the base of the jet, where material is still being launched at high velocity, the conditions may allow for acceleration well beyond what a supernova shock can achieve. The magnetic fields near the compact object can be extraordinarily strong, providing the confinement needed to keep particles bouncing in the acceleration region for longer. Young stellar clusters, like the Cygnus OB2 association, offer yet another mechanism. Individual massive stars drive stellar winds with velocities of thousands of kilometers per second. When many such stars cluster together, their winds collide and interact, creating a complex web of shocks throughout the volume of the cluster. A particle injected into this environment encounters shocks repeatedly, gaining energy incrementally from many different interactions over the millions of years that the cluster remains active. Because the energy input is sustained, these stars live for millions of years and continuously drive their winds. The cumulative acceleration can reach energies that no single supernova remnant achieves. This collective acceleration in stellar clusters has been named the star cluster or OB association PeVatrons scenario, and it is one of the most actively studied theoretical models in the field. The Cygnus cocoon, with its superbubble driven by the winds of OB2, is the best studied example. Other star-forming regions in the galaxy may harbor similar environments. The variation in mechanisms between different PeVatron candidates reflects a broader truth about high-energy astrophysics. There is no single way to achieve extreme particle acceleration. The universe is inventive, finding multiple routes to the same extreme outcome through very different physical systems. Neutron stars, black holes, stellar winds, supernova explosions, all of these can, under the right conditions, drive particles to peta-electron-volt energies. This also means that the cosmic ray spectrum is not produced by a single type of source. It is the superposition of contributions from many different source populations, each operating over different energy ranges and different timescales, distributed throughout the galaxy in patterns that reflect its complex star formation history, its magnetic field structure, and the life cycle of its massive stars. Massive stars are the key drivers in this ecosystem. Stars with masses greater than roughly 8 times the mass of the Sun live fast and die explosively. Their lifetimes are measured in millions of years rather than billions, and they end in core collapse supernovae that release tremendous amounts of energy in a matter of seconds. The compact remnants they leave behind neutron stars and black holes can continue accelerating particles for much longer. Pulsars spin down over timescales of tens of thousands to millions of years, gradually transferring their rotational energy to the particles they accelerate. Neutron stars in binary systems can accrete material from companion stars for much longer still, continuously releasing gravitational energy. A galaxy's cosmic ray budget is therefore closely tied to its history of massive star formation. Galaxies with higher rates of star formation produce more supernovae, more pulsars, and more X-ray binaries per unit time, and should therefore produce more cosmic rays. This connection has been observed. Galaxies with elevated star formation rates, called starburst galaxies, appear to have cosmic ray densities far higher than the Milky Way's, with correspondingly more intense diffuse gamma-ray emission. The Milky Way's own cosmic ray environment reflects its star formation history over the past several billion years. The galaxy has not always formed stars at the same rate. There have been periods of elevated activity, possibly triggered by interactions with satellite galaxies or by instabilities in the galactic disk. The cosmic rays present today carry the accumulated output of all those past episodes of star formation and stellar death. One of the most interesting long-term questions in the field is whether the cosmic ray spectrum varies significantly across different regions of the galaxy. Measurements near the Sun reflect the local cosmic ray environment within a few hundred light years. Whether the same spectrum applies throughout the galactic disk, or whether there are significant variations near spiral arms, in the galactic center region, or in regions far from star formation, is not well established. Such variations would have implications for understanding how cosmic rays propagate and how they contribute to the energy balance of different parts of the interstellar medium. LHAASO and similar observatories can contribute to this question by mapping the diffuse gamma-ray emission from different regions of the galaxy at peta-electron-volt energies, looking for spatial variations that might indicate non-uniform cosmic ray distributions. There is also the question of cosmic ray feedback. As cosmic rays propagate through the interstellar medium, they not only carry energy, they also exert pressure on the gas. This cosmic ray pressure can drive outflows of gas from the galaxy, regulate star formation, and contribute to the overall structure of galactic winds. Understanding the cosmic ray pressure in the Milky Way requires knowing the total cosmic ray energy density and how it varies with position, which in turn requires knowing the sources and their outputs. The link between cosmic rays and star formation is one of the more subtle and far-reaching implications of the PeVatron discoveries. More PeVatrons than expected means more total cosmic ray output than expected, which means more cosmic ray pressure on the interstellar medium than previously assumed. The implications cascade through galactic ecology in ways that researchers are only beginning to trace. The history of cosmic ray research is in many ways a history of instruments enabling discoveries that theory had predicted, but observation had been unable to confirm. Hess's balloon flight was enabled by an instrument, an electrometer sensitive enough to measure small changes in ionization at altitude. The confirmation of high-energy particle showers required the development of sensitive particle detectors on the ground. The identification of gamma-ray sources required space-based observatories that could detect photons above Earth's absorbing atmosphere. The discovery of PeVatrons required a facility as large as LHAASO, at the right altitude, with the right combination of detector types. Each new instrument generation has expanded the observable range of energies and improved the sensitivity at existing energies. The pattern suggests that future instruments will continue to push the frontier further to higher energies, to more sources, to more precise measurements of individual objects. The Cherenkov Telescope Array is the most ambitious of the planned next-generation facilities. Its design draws on decades of development in imaging atmospheric Cherenkov telescope technology, which detects the brief flashes of Cherenkov light produced in the atmosphere when gamma rays interact with air molecules at high altitude. A single such telescope can detect individual gamma-ray events, and an array of them can reconstruct the direction and energy of each event with great precision. The Cherenkov Telescope Array will consist of more than 100 such telescopes at its 2 sites, providing an order of magnitude improvement in sensitivity over existing facilities at energies from a few tens of giga-electron-volts up to hundreds of tera-electron-volts. In the energy range above 1 peta-electron-volt, ground-based air shower arrays like LHAASO remain the most practical approach, because the gamma-ray flux at these energies is too low to detect efficiently with Cherenkov telescopes. The two technologies are complementary. Cherenkov telescopes excel at lower energies and provide excellent angular resolution. Air shower arrays excel at higher energies and provide better coverage of the sky. Combining their data gives scientists access to an unbroken energy spectrum from a few tens of giga-electron-volts to beyond 1 peta-electron-volt, with good sensitivity throughout. This broad coverage is essential for characterizing individual PeVatron sources because the spectral shape across the full range of energies can distinguish between different acceleration mechanisms and particle populations. There is also increasing interest in combining gamma-ray data with radio observations. Many of the sources in the PeVatron catalog are also strong radio emitters, pulsars, supernova remnants, X-ray binaries. The radio emission comes from lower energy electrons through synchrotron radiation, and comparing the radio spectrum with the gamma-ray spectrum provides additional constraints on the electron population and the magnetic field strength in the source. This multi-wavelength approach has long been standard practice in astrophysics, but extending it to the peta-electron-volt regime requires data from the new generation of gamma-ray instruments. The picture of the Milky Way that is emerging from all of these observations is fundamentally more complex and more energetic than what astronomers imagined even 20 years ago. The galaxy is not a simple disk of stars, embedded in a diffuse halo of gas. It is an active, dynamic environment filled with powerful energy sources, supernovae, pulsars, stellar clusters, binary systems, all of them injecting particles and energy into the interstellar medium on a continuous basis. The cosmic rays these sources produce are a major component of the energy budget of the galaxy, comparable in total energy density to the thermal energy of the gas and the energy of the magnetic field. Understanding how all of these components interact, cosmic rays, magnetic fields, gas, radiation, is one of the central challenges of modern astrophysics. The discoveries LHAASO has made in just a few years of operation have sharpened the questions considerably. even as they have expanded the catalog of known sources. More sources mean more data. More data means better models. Better models mean a more accurate picture of how the galaxy actually works. Victor Hess climbed to 5,300 meters in a balloon, measured something he did not expect, and changed the direction of physics. A little over a century later, scientists have built an observatory the size of 190 football fields at more than 4,000 meters altitude in the mountains of China. And they are measuring things that nobody expected. Either more than 75 natural particle accelerators scattered across the galaxy, some of them pushing particles to energies the Large Hadron Collider cannot match. The cosmic rays are still falling. The mystery of where they come from is finally being solved, one gamma-ray photon at a time. And the answers that are coming back are more extraordinary than anyone had the right to expect. It is worth taking a step back and examining the sheer scale of the energies involved in PeVatron physics, because numbers like 1 quadrillion electron-volts are difficult to make intuitive without comparison. An electron-volt is the amount of energy gained by an electron when it moves through an electric potential difference of 1 volt. This is an extraordinarily small unit of energy in everyday terms. 1 electron-volt is roughly 160 zeptajoules, which is 160 multiplied by 10 to the power of -21 joules. A single mosquito in flight carries about 10 billion trillion electron-volts of kinetic energy just by virtue of its mass and speed. Human-scale energies are so much larger than individual particle energies that making the comparison in reverse is more illuminating. The kinetic energy of a single peta-electron-volt cosmic ray proton is roughly equivalent to the kinetic energy of a stone weighing a few micrograms traveling at a few meters per second. That is, one proton, traveling at nearly the speed of light, carries about the same kinetic energy as a speck of dust moving at walking speed. This might sound modest, but remember that a proton is approximately 1,800 times lighter than an electron, which is itself many billions of times lighter than a grain of sand. The ratio of the proton's mass to its kinetic energy at 1 peta-electron-volt is extraordinary. Proton mass corresponds to about 938 mega-electron-volts of rest energy. A peta-electron-volt is 1 billion mega-electron-volts. So a peta-electron-volt proton is carrying kinetic energy more than 1 billion times its own rest mass energy. It is moving at a velocity so close to the speed of light that the difference is measured in fractions that require careful calculation to express. At velocities this close to the speed of light, relativistic effects are extreme. The proton's effective mass, as measured from the rest frame of any stationary object it encounters, is billions of times its rest mass. The time it experiences relative to an external observer is compressed by the same factor. A peta-electron-volt proton crossing the Milky Way from one side to the other, a distance of roughly 100,000 light-years, would experience that journey as taking only a tiny fraction of a second in its own reference frame. Even though 100,000 years would pass for observers in the galaxy, these are not abstract physics facts. They are relevant to the question of cosmic ray propagation. Because high-energy particles experience time dilation, unstable particles that would normally decay in tiny fractions of a second can survive long enough to travel significant distances. Muons, produced in cosmic ray showers at the top of the atmosphere, particles that should decay in 2 microseconds at rest, routinely reach the ground because their high velocities cause time dilation that extends their effective lifetime to many microseconds, as measured by an external observer. The numbers associated with the PeVatrons themselves are similarly staggering. The Crab pulsar rotates 30 times per second and has a diameter of roughly 20 kilometers, yet it contains more mass than the Sunday. The energy released by the Crab supernova in 1054, the event that created the pulsar and nebula, was equivalent to the Sun's total energy output over several billion years, released in a matter of seconds. A fraction of that energy went into spinning up the neutron star that became the Crab pulsar, and the pulsar has been slowly releasing that rotational energy into the surrounding nebula ever since, powering the particle acceleration that makes the Crab nebula a PeVatron today. The numbers associated with stellar clusters are no less extreme. The Cygnus OB2 association contains several hundred massive stars, each with masses ranging from 10 to more than 100 times the mass of the Sunday. The most massive of these stars have surface temperatures exceeding 30,000 degrees Celsius and luminosities more than 1,000,000 times that of the Sunday. They lose mass at rates of 100 trillion kilograms per second through stellar winds, rates that would evaporate Earth's entire mass in less than 200 years. The kinetic energy carried by these winds is channeled, through collisions and shocks, into accelerating the particles detected by LHAASO. X-ray binaries like Cygnus X3 operate at even more concentrated energy scales. The compact object, whether a black hole or neutron star, has a surface gravity millions of times stronger than Earth's. Material falling onto the compact object converts a significant fraction of its gravitational potential energy into radiation. For a neutron star, this efficiency is around 10%. That is, 10% of the rest mass energy of the infalling material is released as radiation. For a black hole with an accretion disk, efficiencies of up to 42% are theoretically possible, depending on the spin of the black hole. For comparison, nuclear fusion in the Sun converts only about 0.7% of mass to energy. The accretion-powered luminosity of an X-ray binary like Cygnus X3 can reach tens of thousands of times the luminosity of the Sun, concentrated in a region only a few kilometers across. The jets launched by the system carry a fraction of this energy outward at relativistic velocities, creating the conditions for the extreme particle acceleration that makes the system a super PeVatron. All of these sources, pulsars, stellar clusters, X-ray binaries, are operating through physics that is well understood in its basic outlines. The equations of general relativity describe the behavior of matter near compact objects. The physics of shocks and magnetic fields in plasma has been studied for decades in the context of solar physics, laboratory plasma research, and astrophysical simulations. Diffusive shock acceleration has been modeled mathematically since the 1970s. What was missing was observational evidence that these mechanisms could actually reach peta-electron-volt energies in real sources. That evidence is now accumulating rapidly. The theoretical framework existed. The instruments to test it did not, until LHAASO was built and turned toward the sky. This is a recurring pattern in astrophysics. Theory often runs ahead of observation by decades, proposing mechanisms and predicting phenomena that cannot be confirmed until better instruments are built. The existence of black holes was predicted by general relativity in 1915 and confirmed observationally by gravitational wave detection in 2015, a gap of a century. The existence of neutron stars was predicted by Fritz Zwicky and Walter Baade in 1934 and confirmed with the discovery of pulsars in 1967. PeVatrons were predicted theoretically long before LHAASO confirmed them observationally. In each case, the confirmation required not just better sensitivity, but a new kind of measurement, a different physical observable that could bypass the limitations of previous approaches. For PeVatrons, the key was the combination of high-altitude location, enormous detector area, and multi-type detection that LHAASO brought together for the first time at sufficient scale. The next breakthrough in cosmic ray physics may follow the same pattern. It may require a measurement type that does not yet exist in sufficient sensitivity. Perhaps neutrino measurements from IceCube Gen 2 that can definitively identify hadronic sources, or perhaps a new type of detector that can measure cosmic ray arrival directions more precisely than current technology allows. Some researchers are exploring the possibility of using the moon as a detector. Ultra-high-energy cosmic rays striking the moon produce radio frequency radiation through a process called the Ascarian effect, where a shower of particles in a dense medium produces coherent radio emission. Radio telescopes on Earth might be able to detect this emission, effectively using the moon as a vast natural detector for the highest energy cosmic rays. The moon's surface area is many orders of magnitude larger than any human-built detector, which would provide sensitivity to event rates too low for any ground-based facility. Other proposals involve large arrays of underwater or under-ice detectors extending beyond IceCube's current volume, satellite-based detectors for ultra-high-energy cosmic rays observed from space, and distributed networks of small detectors using existing infrastructure such as smartphone sensors or repurposed electronics. The spirit behind all of these proposals is the same. The cosmic ray spectrum extends to energies where direct particle detection becomes impractical, and new physical techniques are needed to access those regimes. Each new technique opens a new window on the universe, just as radio astronomy, X-ray astronomy, and gravitational wave astronomy each opened new windows that revealed phenomena invisible at other wavelengths. What those windows will reveal is, by definition, unknown in advance. But the track record of the past century suggests that each new window delivers surprises. Cosmic rays themselves were a surprise. The discovery of pulsars was a surprise. The first detection of a gamma-ray burst was a surprise. The detection of gravitational waves was a confirmation of prediction. But the variety of sources that followed neutron star mergers, asymmetric supernovae, possibly cosmic strings, has been full of surprises. PeVatrons are, in retrospect, not surprising. They were predicted by theory, and the physical mechanisms that produce them are well understood. But the sheer number of them, more than 75 in the Milky Way alone, in the span of just a few years of observation, and the variety of their forms, and the evidence that some of them reach energies far beyond the predicted galactic maximum, are surprising. They change the picture of the Milky Way in ways that have not yet been fully absorbed into the standard models. A galaxy containing more than 75 active PeVatrons is a galaxy producing far more ultra-high energy cosmic rays than the simple models assumed. It is a galaxy whose non-thermal energy content, the energy not carried by thermal radiation but by particles at extreme energies, is larger than previously estimated. It is a galaxy that is more violent, more energetic, and more interesting than it appeared before LHAASO pointed its detectors at the sky. And it is worth remembering that LHAASO can only see the gamma-ray output of these sources, the photons that escape and travel to Earth. The actual energy in cosmic rays is larger, because most of the accelerated particles do not produce gamma rays visible at Earth. They spread throughout the galaxy, losing energy gradually, contributing to the galactic cosmic ray background. The sources LHAASO has detected are the tips of the iceberg. The total cosmic ray output of the Milky Way's PeVatron population is much larger than the gamma-ray observations alone suggest. Quantifying that total output is a goal for future research, requiring better models of cosmic ray propagation and better measurements of the diffuse emission throughout the galaxy. When those measurements are complete, the updated picture of the Milky Way's energy budget will likely be significantly different from the one in current textbooks. The field is also grappling with the boundary between galactic and extragalactic cosmic rays. The transition between these two populations, thought to occur somewhere between the cosmic ray knee and the ankle, is not a sharp line. Galactic sources contribute most of the cosmic rays below the knee. Extragalactic sources dominate above the ankle. In between is a region of uncertainty, where both populations overlap and their relative contributions change with energy. The composition of cosmic rays in this transition region, whether the particles are mostly light elements like hydrogen and helium, or heavier elements like iron, carries information about the source populations. Lighter elements point toward extragalactic sources that accelerate protons to very high energies. Heavier elements are more consistent with galactic sources that accelerate nuclei, which can reach higher rigidity equivalent energies for the same total energy. Measurements of composition in this energy range are technically challenging, and results from different experiments have sometimes been inconsistent. Resolving these inconsistencies requires better particle identification at high energies, which is one of the goals of next-generation detector arrays. The Milky Way's contribution to cosmic rays above the knee, including contributions from super PeVatrons like Cygnus X3, may extend the galactic contribution higher in energy than previously thought, changing the balance between galactic and extragalactic sources in the transition region. Whether this makes the extragalactic source identification problem easier or harder depends on how significantly the galactic contribution changes the energy spectrum in that regime. These are not abstract puzzles for theorists. They are observational questions that current and planned instruments are designed to answer. The next decade of data from LHAASO, the Cherenkov Telescope Array, IceCube, Gen 2, and complementary facilities will substantially constrain the galactic-extragalactic transition, the composition of cosmic rays at high energies, and the contribution of different source types to different parts of the spectrum. The century-long mystery that Victor Hess stumbled into during his balloon flight in 1912 is being systematically unwound. Not all at once the highest energy sources, the extragalactic contributors, the propagation pathways, the composition at every energy. These will take years or decades more to fully understand. But the trajectory is clear. More instruments, better instruments, more data, more understanding. For now, the Milky Way has revealed itself to be a place where nature routinely builds particle accelerators of extraordinary power, scattered through its disk and its spiraling arms, accelerating particles to energies that challenge our most powerful machines and our most sophisticated theories. The cosmic rays falling on Earth today are the output of this galactic machine, a machine that has been running since long before any human looked up and wondered what was out there. The answer, it turns out, is far more than anyone expected. There is another dimension to the story of cosmic rays that rarely gets attention but is increasingly relevant: the connection between cosmic rays and life itself. Earth's biological history has unfolded in a continuous bath of cosmic radiation. For the entirety of multicellular life's existence, roughly 600 million years, cosmic rays have been striking the atmosphere, producing secondary particle showers, and sending muons and other energetic particles through every living organism on the planet. This has not been without consequence. Ionizing radiation from cosmic ray showers contributes to the background radiation dose that every living organism receives. At sea level, this cosmic contribution accounts for roughly 10% of the annual radiation dose for humans, similar to the contribution from radon gas in the ground, and a few times less than the dose from internal sources like potassium-40 in the body. The cosmic contribution is higher at altitude. Pilots and flight crew on long-haul international routes receive several times the cosmic ray dose of people at sea level, accumulating over the course of a year an additional dose comparable to a medical X-ray. At extreme altitudes, the dose rises further. Astronauts in low Earth orbit, where they are partially shielded by Earth's magnetic field, receive cosmic ray doses roughly 100 times higher than at sea level. On a trip to Mars, outside Earth's magnetic field and without the shielding of an atmosphere, cosmic ray exposure would be a significant health consideration for the crew. But the deeper connection between cosmic rays and life is not about chronic radiation exposure. It is about mutation and evolution. Cosmic rays cause DNA damage. When a high-energy particle or its secondary products pass through a cell, they can ionize atoms in DNA molecules, breaking chemical bonds and creating strand breaks. Most of this damage is repaired by cellular mechanisms evolved to handle the constant background of cosmic and terrestrial radiation. But some damage escapes repair, becomes a permanent mutation, and is passed on to daughter cells. Over evolutionary timescales, some of these mutations are harmful, some are neutral, and some rarely are beneficial. The background rate of cosmic ray-induced mutations is one input into the overall mutation rate that drives the variation on which natural selection acts. This does not mean cosmic rays are responsible for evolution. The mutation rate from other sources, including molecular errors during DNA replication, reactive oxygen species from metabolism, and ultraviolet radiation from the sun, is much larger. But cosmic rays are part of the physical environment in which life has evolved, and they have been doing so for as long as complex life has existed. There have been periods in geological history when Earth's cosmic ray exposure was elevated. Nearby supernova explosions, occurring within a few hundred light-years, could significantly increase the flux of cosmic rays reaching Earth for thousands of years. The geological record contains evidence of elevated cosmic ray exposure associated with enhanced production of cosmogenic isotopes, radioactive atoms produced when cosmic rays interact with atmospheric molecules. Some researchers have suggested that such events may have influenced mass extinctions or biological radiation events, though the evidence for a direct causal link is not established. What is established is that the cosmic ray flux has not been constant over Earth's history. The galactic environment has changed. The Sun has moved through different parts of the Milky Way, encountering regions with different stellar densities, different supernova rates, and different cosmic ray intensities. The Milky Way itself has had periods of more active star formation, producing more supernovae and more cosmic rays. The PeVatrons discovered by LHAASO are the current active sources of the highest energy cosmic rays in the galaxy. They are part of a system that has been operating in various forms for billions of years. The particular sources are different stars form, age, and die. Supernova remnants expand and dissipate. Stellar clusters disperse. But the overall population of accelerators has been maintained by continuous star formation throughout the galaxy's history. Understanding the current PeVatron population is therefore a window into the galactic system that has shaped Earth's cosmic environment over geological time. The question of how the cosmic ray flux at Earth has varied over millions of years, and whether those variations are correlated with any features of the biological record is a genuinely interesting one, even if the answers are likely to be subtle and difficult to establish with confidence. On a much shorter timescale, cosmic ray variability is well documented. The Sun's magnetic activity modulates the flux of lower-energy cosmic rays at Earth. During periods of high solar activity, the stronger solar magnetic field and increased solar wind partially shield Earth from cosmic rays below a few giga-electron-volts. This 11-year cycle of solar modulation is clearly visible in cosmic ray detectors at the surface. Cosmic rays above a few hundred giga-electron-volts are not significantly affected by solar modulation and arrive at roughly constant rates regardless of solar activity. Solar flares and coronal mass ejections can temporarily increase the low-energy cosmic ray flux through a process called a solar energetic particle event. These events are distinct from galactic cosmic rays. They are produced by the Sun itself, but they demonstrate that the cosmic ray environment at Earth is dynamic, even on human timescales. The relevance of all of this to the PeVatrons story is that the highest energy cosmic rays, those at and above the knee, are the ones least affected by solar modulation and most directly connected to galactic sources. They arrive at roughly constant rates, carrying information about the long-term output of their sources. When LHAASO detects a peta electron-volt gamma ray from a given direction, it is measuring the sustained output of whatever object produced it, integrated over the time it took the photons to travel from the source to Earth. For a source like the Crab Nebula, 6,500 light-years away, the photons arriving today were emitted roughly 6,500 years ago. The pulsar has been continuously accelerating particles for almost 1,000 years since the supernova of 1054, and will continue to do so for tens of thousands of years into the future as it slowly spins down. The gamma ray signal LHAASO measures is a snapshot of a sustained, ongoing process. For more variable sources like Cygnus X3, with its 4.8-hour orbital modulation and intermittent flares, the situation is more complex. The photons arriving from 5,000 light-years away were emitted 5,000 years ago, but the current behavior of the system can still be studied because the orbital and flaring timescales are short compared to the light travel time. Variations observed today correspond to events that occurred 5,000 years ago, but relative to each other, the sequence of events is preserved, and the physics can be studied in the same way. This temporal offset between observation and emission is a fundamental feature of astronomy at any wavelength. It means that observing distant objects always means looking into the past. For relatively nearby galactic sources, the past in question is tens of thousands of years well within recorded human history for the closest sources, and extending to the time of the first agricultural civilizations for sources at a few thousand light-years. The photons from the Crab Nebula supernova that would have been visible in 1054 are still traveling outward, having now passed beyond thousands of light-years. The photons being detected by LHAASO today from the Crab Nebula left it roughly 6,500 years ago, around the time of early Mesopotamian civilizations. These are not just poetic observations. They are relevant to the scientific analysis of variable sources, where understanding the relationship between different observations requires accounting for light travel times and for the way in which the source physics connects the different wavelength emissions that travel to Earth simultaneously or at different times. The multi-messenger approach, combining gamma rays, X-rays, radio waves, neutrinos, and potentially gravitational waves from the same source, benefits from this careful accounting. When LHAASO detects a gamma-ray flare from a binary system at the same time that an X-ray telescope detects an X-ray flare from the same object, the two signals left the source simultaneously, carrying simultaneous information about the state of the system. Correlating such multi-wavelength flares is one of the most powerful tools for identifying the physical mechanisms driving the emission. LHAASO has already demonstrated this capability with Cygnus X3, where the 4.8-hour periodicity in gamma rays match the periodicity seen in X-rays and infrared, all three wavelengths carrying simultaneous information about the orbital dynamics of the binary system. Future observations, with more sensitive instruments and more extensive monitoring campaigns, will enable similar analyses for a much broader range of sources. There is also scientific value in monitoring known sources over long time periods. The catalog of more than 75 PeVatrons is a snapshot of the galaxy's energetic activity at the current epoch. Some of these sources will change on timescales of years to decades. Pulsar spin-down rates gradually shift, binary star systems evolve, supernova remnants expand and cool. Monitoring these changes as they happen provides a direct window into the dynamics of particle acceleration over human observable timescales. LHAASO and other observatories are designed for this kind of long-term monitoring. Unlike a targeted space telescope that must be pointed at specific objects, ground-based air shower arrays observe the entire overhead sky simultaneously, continuously. Every source within their field of view is monitored at all times. Any flare, any increase in emission, any change in spectral shape is captured automatically. This continuous coverage is one of LHAASO's greatest strengths as a discovery instrument. The combination of a wide field of view, continuous monitoring, and excellent sensitivity at peta-electron-volt energies has already produced the discoveries described here. As the observatory continues to operate and accumulate more data, the statistical significance of existing measurements will increase. New transient events will be captured, and new sources at the edge of detectability will emerge from the noise. The science of cosmic rays has been transformed in less than a decade by a single observatory. What previous generations of instruments could not resolve in a century, LHAASO is systematically addressing in years. Not because the physics changed, but because the instruments finally matched the scale and precision demanded by the problem. This is the nature of discovery at the frontier of observational science. The universe does not reveal itself gradually and smoothly. It waits for the right instrument to be pointed at the right part of the sky, and then it delivers answers at a pace that can be difficult to keep up with. The PeVatron catalog going from 0 to 75 in a few years is a vivid illustration of this pattern. What comes next will be determined by the instruments now under construction, the data now being analyzed, and the questions now being asked. Some of those questions will turn out to be the wrong questions that has happened before in cosmic ray physics, and it will happen again. But the accumulation of high-quality data, the development of better theoretical models, and the expansion of international collaboration all point toward a field that is poised for continued rapid discovery. The mystery that Victor Hess's balloon flight, revealed in 1912, is not fully solved. The sources of the highest energy cosmic rays, above the ankle, remain largely unidentified. The precise physical mechanisms driving acceleration in individual PeVatrons are still being worked out. The contribution of different source populations to different parts of the spectrum is not fully established. The composition of cosmic rays in the energy range of the knee remains imprecisely known. But the era in which these were open questions with no observational anchor is over. LHAASO and its collaborating observatories have given scientists dozens of specific, identifiable sources to study, each one a natural laboratory for extreme particle physics, each one contributing data that constrains the theoretical models. The path from confusion to understanding is now visible, even if the journey is not complete. The most powerful natural particle accelerators in the galaxy are no longer hypothetical. They are cataloged, they are being monitored, and they are yielding their secrets one gamma-ray photon at a time. The cosmic rays they produce have been visiting Earth since before any instrument existed to detect them. Now, finally, we can follow the trail back to where they came from. There is one more aspect of this story that deserves careful attention. The remarkable fact that nature has independently arrived at peta-electron-volt acceleration through such different physical systems. Consider how different the Crab pulsar is from Cygnus X3. The Crab pulsar is an isolated neutron star, created by a supernova nearly 1,000 years ago, spinning 30 times per second in the middle of a cloud of gas and magnetic field that it continuously energizes with its rotation. There is no companion star, no accretion disk, no jet. The energy comes from the stored rotational energy of the neutron star, slowly being radiated away through the particle wind it drives. Cygnus X3, by contrast, is a binary system where a compact object, likely a black hole, orbits a massive Wolf-Rayet star every 4.8 hours. Material flows from the star to the compact object, releases gravitational energy as it falls inward, and powers jets of plasma that stream outward at relativistic velocities. The energy source is gravitational, not rotational. and the system is constantly fed by the donor star's wind. The Cygnus OB2 association is different from both. It is not a single compact object or binary system. It is a collection of hundreds of massive stars, all alive simultaneously, each driving stellar winds, with those winds colliding and creating a web of shocks throughout the volume of the cluster. No single star in the cluster is a PeVatron. The PeVatron nature emerges from the collective behavior of the whole system. These three systems, a spinning neutron star, a mass-transferring binary, a stellar cluster, have almost nothing in common physically. Yet all three produce gamma rays at peta-electron-volt energies. The conclusion is that peta-electron-volt particle acceleration does not require one specific type of extreme environment. It requires certain general conditions: sufficient energy input, sufficient magnetic field strength for confinement, and sufficient time for the acceleration to operate. These conditions arise independently in many different astrophysical contexts. The galaxy, over its billions of years of evolution, has found multiple ways to create the right conditions in multiple places simultaneously. The current catalog of more than 75 PeVatrons reflects this diversity: pulsars, pulsar wind nebulae, supernova remnants, stellar clusters, X-ray binaries, and possibly other types of sources not yet clearly categorized. Each type of source provides a different window into the physics of extreme acceleration. Pulsars let scientists study how rotational energy is converted to particle energy in a clean, isolated environment. Binary systems reveal how gravitational energy and jet physics drive acceleration. Stellar clusters demonstrate collective effects and the role of sustained, distributed energy input. Studying all of them in parallel gives scientists a more complete view of the physical principles at work. The diversity also has implications for the cosmic ray spectrum. Different source types accelerate different particle types to different maximum energies with different spectral shapes. The spectrum of cosmic rays arriving at Earth is the convolution of all these different contributions, smeared together by propagation effects. Disentangling them requires understanding each source type well enough to predict its contribution, then checking whether the sum matches the observations. This is a complex, multi-step problem that will occupy researchers for years to come. Progress requires advances on multiple fronts simultaneously. Better observations of individual sources to constrain their spectra. Better propagation models to predict how particles spread from sources to Earth. Better composition measurements to test predictions about the relative contributions of protons and heavier nuclei, and better measurements of the diffuse gamma ray emission to test models of the overall galactic cosmic ray population. The infrastructure for all of this work is being built now. LHAASO continues to operate and expand its dataset. The Cherenkov Telescope Array is under construction. IceCube Gen 2 is in the planning phase. Proposed space-based observatories for ultra-high-energy cosmic rays are being designed. The scientific collaboration needed to analyze and interpret all of this data is growing, with research groups from dozens of countries contributing to the effort. The field has reached an unusual moment in its history. For most of the century since Hess's discovery, cosmic ray research was constrained by a lack of data. The sources were unknown, the trajectories were scrambled, and the available detectors could only measure aggregate properties of large numbers of particles rather than identifying specific sources. Theory was ahead of observation, and theorists could only propose candidate source types without knowing which of them, if any, were actually responsible. Now, observation is beginning to catch up with theory. The PeVatron catalog is real. The gamma ray spectra of individual sources are being measured. The connection to neutrino emission is being probed. The diversity of source types is becoming clear. Theorists now have specific targets to explain, and the explanations are being tested against increasingly precise data. This is how science is supposed to work. Theory proposes, observation tests, and the combination drives understanding forward. For cosmic ray physics, the observational side was missing the essential tool, a large enough detector, in the right location, with the right sensitivity, for more than a century. LHAASO provided that tool, and the field has not been the same since. The next generation of tools will provide further advances. When IceCube Gen 2 can definitively identify hadronic sources through neutrino emission, it will confirm which PeVatrons are actually responsible for cosmic rays and not just for electron acceleration. When the Cherenkov telescope array measures the spectra of individual sources with unprecedented precision, it will constrain the acceleration physics in ways that are not currently possible. When proposed space observatories detect the highest energy cosmic rays with better angular resolution, it will become possible to identify individual source candidates for the most extreme particles. Each of these advances will refine the picture further. The cosmic ray spectrum, from the lowest energies to the highest, will eventually be explained in terms of specific identified source populations, operating through known physical mechanisms, producing particles that propagate through the galaxy in ways that are well modeled and well tested. That complete picture does not yet exist, but it is being assembled, piece by piece, gamma ray by gamma ray, one extraordinary detection at a time. The universe has been accelerating particles to extreme energies since the first massive stars formed and exploded billions of years ago. The cosmic rays produced by those ancient events are long since lost to time, their energies dissipated, their particles absorbed or scattered into undetectably low energies over the billions of years since. But the sources that produce them are still operating in new generations of stars and compact objects, continuously replenishing the galactic cosmic ray population. The cosmic rays arriving at Earth today are the latest output of a system that has been running since before the solar system formed. They carry energy from some of the most extreme environments in the galaxy, delivered here by the fundamental physics of charged particles moving at nearly the speed of light. They pass through the atmosphere, they ionize the air, they produce secondary showers, and then most of them are absorbed and their energy deposited. A tiny fraction of that energy goes into the instruments that allow scientists to detect and measure them. From those measurements, scientists are reconstructing the sources. From the sources, they are understanding the mechanisms. From the mechanisms, they are building a picture of the galaxy's energy systems that would have seemed impossibly detailed to Victor Hess, floating in his balloon in 1912, watching his electrometer register 3 times the ionization he expected. He did not know what was ionizing the air around him. He suspected it came from space, and he was right. 114 years later, we know not only that it comes from space, but which objects in space are responsible, how those objects work, and what happens to the particles from the moment they leave their source to the moment they arrive at the instruments that detect them. That is the measure of how far the field has come. And, given the pace of the last 5 years, it is a reasonable expectation that the next 5 years will bring comparable advances, more sources, more mechanisms, more precise measurements, and perhaps the first confirmed hadronic PeVatrons, the sources most directly responsible for the cosmic rays that Victor Hess stumbled upon on a clear day in 1912, ascending through the thin air above Austria in a wicker basket suspended from a balloon. The mystery is not fully solved. But it is being solved rigorously and systematically by a generation of instruments and scientists who finally have the tools the problem demands. One of the most underappreciated aspects of the PeVatron story is the role that serendipity continues to play, even in the era of purpose-built detectors and carefully planned observing campaigns. LHAASO did not discover its first major result after years of painstaking observation. It found an abundance of gamma rays, with energies exceeding 1 peta-electron-volt within the first 6 months of partial operation, before the detector was even fully constructed. This was not the expected pace of discovery. The team had anticipated a longer path to first results. The universe, it turned out, was not only full of PeVatrons, it was eager to show them. This kind of unexpected productivity at the start of an observatory's life has historical precedent. When the first X-ray astronomy mission, Uhuru, launched in 1970, it rapidly cataloged hundreds of X-ray sources that had not been expected in such numbers. When the Fermi Gamma Ray Space Telescope launched in 2008, its first catalog of gamma-ray sources included many objects of completely unexpected types. New instruments frequently deliver more than their designers anticipated because the universe is richer than any model predicts. The reason this keeps happening is straightforward. Models are built from existing observations, which are inevitably limited by the capabilities of previous instruments. When a new instrument extends the observable range in energy, in sensitivity, in sky coverage, it accesses phenomena that were genuinely undetected before, not just unresolved or uncertain. LHAASO's extension of gamma-ray detection to peta-electron-volt energies at high sensitivity was a genuine expansion of the observable universe, and it found things there that existing models had underestimated. This is not a criticism of previous models. The models were correct given the data available. What the new data revealed is that the universe was more active, more energetic, and more populated with extreme objects than the data could previously support. This is the normal, healthy operation of empirical science. Models constrain what we expect given what we know, and new observations expand what we know. The expansion of the PeVatron catalog from 0 to more than 75 in a few years has created a situation where the theoretical community is actively working to absorb the implications. New models are being developed. Old models are being revised. Some candidate explanations that seemed plausible before the observations are now inconsistent with the data and have been abandoned. Others have been strengthened. A few phenomena have been observed that were not predicted by any existing model and represent genuinely new theoretical challenges. One such challenge is the very high rate of super-PeVatron activity. If Cygnus X3, a single binary system, is capable of accelerating protons to at least 10 peta-electron-volts, and if similar systems exist throughout the galaxy, then the contribution of X-ray binaries to the cosmic ray flux at and above the knee may be larger than standard models assumed. How large that contribution is depends on how many such systems exist and how long they remain active as super-PeVatrons questions that require both more observations of Cygnus X3 itself and a broader survey of similar processes. Binary systems. Another theoretical challenge involves the transport of high-energy particles from their sources through the interstellar medium. Standard propagation models, based on decades of cosmic ray data, assume that the diffusion of cosmic rays through the galaxy is relatively uniform particles spreading out smoothly from their sources in all directions, governed by the large-scale structure of the galactic magnetic field. But observations of extended gamma-ray halos around several pulsars' glowing regions of emission, extending far beyond the pulsar wind nebula itself, suggest that diffusion near some sources is much slower than standard models predict. In these halos, cosmic rays appear to be confined close to the source for longer than expected, leading to enhanced emission in the surrounding region. Understanding why diffusion is slower in some regions than others requires a better understanding of the turbulent structure of the galactic magnetic field on small scales. This is an active area of research, connecting observations of specific sources like these pulsar halos to the broader theoretical problem of how magnetic turbulence governs cosmic ray transport. The galactic magnetic field itself is one of the least well-constrained inputs in cosmic ray physics. Its large-scale structure, the spiral component, the toroidal halo component, the random turbulent component, is known approximately from observations of the polarization of radio emission from pulsars and from synchrotron radiation surveys. But the small-scale turbulent structure, which governs diffusion on the scales relevant to cosmic ray propagation from individual sources, is poorly constrained observationally. Better measurements of the magnetic field structure, combined with better models of how it affects cosmic ray transport, would substantially improve predictions of how the cosmic ray spectrum relates to the distribution and output of specific source types. Space-based instruments designed to map the galactic magnetic field through measurements of dust polarization and synchrotron emission are being proposed and in some cases developed. Combining their results with the gamma-ray observations from LHAASO and the Cherenkov telescope array, and with the neutrino observations from IceCube and eventually IceCube Gen 2, would provide the most comprehensive picture yet of the galactic cosmic ray ecosystem. The sheer scale of the scientific program that has been opened up by LHAASO's discoveries is remarkable. A single observatory, operating for a few years, has identified dozens of new sources, confirmed the existence of a long-predicted class of objects, changed the picture of the Milky Way's energy budget, and created new theoretical challenges that will occupy researchers for years. It has done this by going where previous instruments could not reach the peta-electron-volt energy regime and finding what was waiting there. What will be waiting at even higher energies above 10 peta-electron-volts, above 100 peta-electron-volts, into the exa-electron-volt regime, where galactic and extragalactic sources overlap is not yet known. The observations needed to find out do not yet exist. building the instruments to make those observations is the challenge of the next decade. It is a challenge that the astrophysics community is taking seriously. Proposals for next-generation ground-based arrays at peta-electron-volt and beyond energies are being developed in multiple countries. The scientific case for these instruments is strong, grounded in the discoveries LHAASO has already made and in the clear theoretical motivation for what lies at higher energies. The story that began with a physicist in a balloon over Austria in 1912 continues to unfold, one discovery at a time, one instrument generation at a time. The particle that ionized the air around Hess's electrometer and launched a century of research was just the messenger. The story is about where it came from and how it got there, and what it tells us about the most extreme places in the universe. Those places are no longer entirely mysterious. They have names: Messier 1, Cygnus X3, Cygnus OB2. They have measured energies, detected gamma rays, identified periodicities, and cataloged emission profiles. They are specific, real objects in a specific, real galaxy, producing particles at energies that no human technology has achieved, delivering them here, to a planet that has been bathed in their output for its entire history. That is the story of cosmic rays. It is a story about energy at the most extreme scales nature allows, produced by some of the most violent processes in the universe, delivered quietly and continuously to a planet that for most of its history had no idea it was happening. Now, finally, we do. And the investigation is just getting started. There remains one question that scientists consistently return to when discussing the future of PeVatron research. What is the absolute maximum energy that nature can produce in a particle? The GZK limit, at around 50 exa-electron-volts, imposes a practical ceiling on the distance over which ultra-high energy protons can travel. But it does not impose a ceiling on energy production at the source. A source could, in principle, accelerate protons to arbitrarily high energies, so long as there are particles to accelerate and energy to drive the process. The limit on how far those particles travel before losing energy to the cosmic microwave background is a separate constraint from the limit on how much energy a source can impart. Within the Milky Way, the practical maximum is likely well below the GZK energy. The magnetic confinement that allows particles to be accelerated in shocks requires that the gyro radius of the particle be smaller than the acceleration region. For peta-electron-volt protons, the gyro radius in typical galactic magnetic fields is already comparable to the size of the larger PeVatron environments. Above 10 peta-electron-volts or so, galactic magnetic fields can no longer confine protons, and they escape before accumulating further energy. This is part of why Cygnus X3, with its compact, highly magnetized environment near a black hole, can reach energies above 10 peta-electron-volts, while most galactic sources cannot. For extragalactic sources, active galactic nuclei, gamma-ray bursts, galaxy clusters, the scales, and magnetic field strengths are much larger, and much higher energies are achievable in principle. The most energetic cosmic rays ever detected, above 100 exa-electron-volts, must come from extragalactic sources given the GZK constraint on propagation distance. What those sources are, exactly, remains one of the most important open questions in astroparticle physics. The Telescope Array experiment in Utah and the Pierre Auger Observatory in Argentina are the two largest current detectors focused on ultra-high energy cosmic rays above the GZK threshold. Both experiments have produced catalogs of arrival directions for the highest energy events, and both see hints of anisotropy, slight deviations from a uniform distribution across the sky that might point towards specific source regions. But the statistics are still limited, and no individual source has been confirmed. The Pierre Auger Observatory, covering 3,000 square kilometers of the Argentinian Pampa, is the world's largest cosmic ray detector by area. Its detectors combine water Cherenkov stations spread across the vast Pampa with fluorescence telescopes that observe the ultraviolet glow of air showers on dark, clear nights. By combining both techniques, it can measure the energy and direction of the highest energy cosmic rays with good precision. Proposed upgrades to the Auger Observatory aim to improve composition measurements at the highest energies, which would provide additional constraints on which types of sources are responsible. One intriguing candidate for the sources of ultra-high energy cosmic rays is the class of objects called Seyfert galaxies. active galaxies with moderately luminous central black holes that drive powerful outflows without the extreme luminosity of quasars. The central regions of Seyfert galaxies can produce jets and winds that interact with the surrounding interstellar medium, creating conditions that might accelerate particles to exatel electron-volt energies. There is some observational evidence from Auger data for an excess of ultra-high-energy cosmic rays from the direction of Seyfert galaxies within a few hundred megaparsecs, but the association is not yet statistically definitive. Gamma-ray bursts, the most luminous explosions in the universe, are another candidate. A typical long gamma-ray burst releases more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. The extreme conditions in the jet of a gamma-ray burst, relativistic velocities, intense magnetic fields, enormous energy input are theoretically capable of accelerating particles to the very highest energies. But gamma-ray bursts are rare and short-lived, and their contribution to the steady flux of ultra-high-energy cosmic rays arriving at Earth is uncertain. These questions are connected to the PeVatrons story through the broader framework of particle acceleration physics. The mechanisms at work in galactic PeVatrons shock acceleration, magnetic reconnection, collective wind effects are versions of the same mechanisms operating in extragalactic sources, just at different scales and energy inputs. Understanding the galactic sources in detail provides a foundation for modeling extragalactic sources at even more extreme energies. The PeVatron era has therefore opened a window not only into the galaxy's high-energy physics, but into the astrophysics of extreme particle acceleration across all scales. The catalog of galactic PeVatrons, the identification of super PeVatrons like Cygnus X3, and the development of multi-messenger techniques for studying them. All of these are steps toward the broader goal of understanding how particles reach the highest energies achievable in the universe. That broader goal will take decades to achieve. It requires not just better instruments, but a maturation of theoretical understanding, more sophisticated simulations, and the kind of sustained, systematic observational program that only becomes possible once the basic phenomenology is established. LHAASO and its generation of instruments have established that basic phenomenology for galactic PeVatrons. The next generation will do the same for super PeVatrons and eventually for the extragalactic sources of the most extreme cosmic rays. In the meantime, the particles keep arriving. On a typical day, roughly 10,000 cosmic ray particles strike each square meter of the top of Earth's atmosphere. Most of them are at low energies, giga-electron-volt protons, helium nuclei, and heavier elements that have been drifting through the galaxy for millions of years, losing energy gradually, before finding their way to the inner solar system and eventually to Earth. A small fraction are at much higher energies. And an extraordinarily small number, perhaps 1 or 2 per square kilometer per year at peta-electron-volt energies, 1 per square kilometer per century at much higher energies, are the particles that LHAASO and the Pierre Auger Observatory are designed to catch. Each one of those rare high-energy arrivals is a message from one of the most extreme environments in the universe. Tracing that message back to its source, understanding what produced it, and explaining how it traveled to Earth is the work of the field that Hess accidentally founded when he floated above the clouds in 1912 and found the air more ionized than it should have been. The answer, unfolding slowly and now rapidly, is that the universe is full of extraordinary machines, pulsars, black holes, stellar clusters, binary systems all running continuously, all contributing to the river of high-energy particles that flows through the galaxy. Earth sits in that river, has always sat in that river, and is only now beginning to understand the currents that move through it. The science is not finished. The catalog is not complete. The mechanisms are not all understood. The spectrum is not fully explained, but the tools now exist to make real progress on all of these fronts, and the pace of that progress over the last few years gives good reason to expect that the next decade of cosmic ray research will be among the most productive in the field's history. The cosmic rays are still falling, the sources are being found, the physics is being worked out, and the picture of the Milky Way that is emerging from all of this energetic, active, full of particle accelerators far beyond anything human technology can match, is one of the most striking revisions to our understanding of the galaxy in a generation. That revision is not complete, but it is well underway. And it began with a physicist, a balloon, and an electrometer reading 3 times higher than expected at 5,300 meters above Austria on a summer day in 1912.